Hi, everyone. Welcome to today's webinar. This is the next webinar in our series of webinars supporting Formula SAE and similar competitions like Baja and Supra. I am really excited about this one because personally, I used to teach power transmission design as a professor, and I had students do the math with Excel spreadsheets, lots and lots of Excel spreadsheets. And then I started working at Hexagon and I found out about Romax, and I was just shocked by how much it can streamline. And so I think it will really unlock abilities for teams, especially as they're getting into things like EV power transmission design. If you want to design things with planetary gearboxes, I know how difficult that can be. Romax really makes it not be that heavy of a lift. And to show you how Romax can connect to Formula and to take you through a sample workflow, we have Reese Jones with us today. He's an engineering manager, so he covers Romax usage in the Europe, Middle East, and Africa region. So they provide support and training services to customers. Romax is actually short for rotating machinery experts, right? So it's the name of the product, but it's also a name that's applicable to the people at the company who have rotating machinery expertise and help customer companies actually design power transmissions. So Reese has a background in transmission analysis. He has a PhD in the mathematical modeling of gearbox vibrations, and he has 6 years of experience in motorsport transmissions. I struggle to think of somebody who would be more qualified to give this talk. Reese, I'll hand it over to you. Thank you so much for preparing this webinar and offering it today.
No problem at all, and thank you very much for the introduction there. So yeah, welcome everyone to this session on Romax and its applicability to Formula SAE. What we'll do is we'll have a first introduction to Romax, where it sits within the marketplace for analysis of transmissions, and a little bit of talk about how it does that and how it's found its niche market within that space. But what I want to spend most of my time doing is to actually do a live demonstration to show you how you can pick up the software quite easily and start building real models. And there's a lot of knowledge already embedded in the software to make things as simple as possible. So the way I'm going to do that is to model a general planetary reduction system, quite a complex one if you're trying to do it from scratch, with an electric machine in there. So almost like a wheel reducer unit that you might put into a hub of a race car. And then finally, we're going to go on to how you can get your hands on the software, where you can find tutorials and get started, and also a bit of a plug for the Romax community that we're trying to build up to allow students to discuss with each other their usage of the software and try and help each other out with the usage as well. And then, as I said, we'll finish off with a question and answer session to cover any topics that I've brought up during the session, or to any other topics that are burning at the moment for you. So, as Alex mentioned, Romax stands for Rotating Machinery Expert, and it was a software that was developed over 35 years ago. And our founder used to work in the bearing industry, and he was a bit frustrated with the fact that when he came to analysing bearings, you would just take a bearing in isolation, apply a force to it, maybe a bit of misalignment, and see how it performed. And he was really interested in taking that approach to a more system level analysis. So including the shafts, including the housings and the gears, and understanding how their deflections impacted the performance in a complete system. And it's grown over those 35 years. And we are now used in I'd probably say 80 or 90% of all motor OEMs to design their transmissions. And also we also delved a few years back into the area of wind renewable energy. And Romax has a dedicated software called Romax Wind, which is used for designing wind turbine gearboxes. And it's a very specialist tool that allows you to certify your gearbox for wind applications, so people can design it and make it right first time when they're designing their transmissions. So, as a designer or in a design process, you might start with a completely blank piece of paper, And then you might want to start by looking at different concepts, different arrangements of transmissions, and starting to get some early engineering insight into the cost benefit of those different systems. And then as that design evolves, you start making decisions, you start adding some more information. You want to get more information out of that software. You want to be able to start making educated decisions on the design of gears, on the selection of bearings, on do you want to apply preload to your bearings, what types of bearings you want to use. You might want to also include electric machines to understand how they might affect your performance. And while you're adding all that detail, you're mainly looking at durability. Is it going to last the duty cycle that I'm providing? Efficiency, especially with EVs at the moment where range is such a key topic. Being able to eke out as much efficiency from your gearboxes is incredibly important. And the final one is vibration and harshness, NVH, and understanding the noise that the gearbox will generate. And the idea is that Romax would sit at the heart of this and allow you to progress your design through the design phases, but also through the analysis phases in the software. And how does it do that? How does it sit within that space? Now, Alex was talking about how he used to give his students spreadsheet after spreadsheet after spreadsheet of hand calculations. You can do all those things, but quite often they take a simplistic approach to the analysis. They don't consider the different physics that are going on. They don't consider the interaction of components. So you might just want to do a gear rating. You want to understand the durability of a gear. You can provide all the information, but you don't understand it from a system level in your analysis. You also have on the other end of the scale, you have generic tools such as finite element tools or multi-body dynamic tools, which are brilliant at solving lots of complex problems. But for a transmission design, they can be very difficult to set up correctly and deal with all the contacts which are occurring within your transmission. They can also be quite slow, again, because they're using general solvers. They can be slow to converge and provide a solution. And then when you've done all that analysis, it's difficult to actually obtain useful information from the results. Like you can get a stress from an FE analysis, but what does that mean in terms of the durability of your gear? Will it withstand your load case? So the idea of Romax is it sits in the middle of these two ends of the spectrum, where it gives you the right amount of detail, the right amount of complexity, but isn't overly cumbersome and allows you to predict results very quickly. So how does Romax do this? Well, we can take a gearbox and we can split it up into its component parts. And at different components, we can give different levels of detail. So for example, on this well, to be quite frank, luckily for us, this is quite similar to the transmission that I'm going to demonstrate shortly. We have within here a planetary system arrangement. So these grey shafts here, the underlying principle of those that you'll know from your engineering degrees, it will be a Timoshenko beam. So it's quite a simple, lightweight solution for working out the deflections of the shafts. Within the gears, we have analytical models that allow the fast calculation of the forces and understanding the stiffnesses of the gear components. And then when we come to bearings, I mentioned that our founder was from the bearing industry. So one of the key drivers for Romax is having the best models for understanding bearing stiffnesses, bearing behaviors, bearing stresses within our models. So we have very robust formulae for defining the stiffnesses of these components, but is also very, very quick at solving. We also have electric machines that we can include into our model, applying forces and also excitations for NVH analysis. And then when we come to more complex components, so in this case, they talk about the housing of the part, we can bring in FE components and use them where they're required. Now, we don't use the FE component in its full. we create super elements of those components because we really are interested in the stiffness that it brings to the system, and how that affects our results. And obviously, when we do create a super element, then it becomes a lot quicker to run our analysis. So here we can see where we introduce excitations from our electric machine, where we can calculate the contact distribution within gears, how we can look at the deflections in FE components, and how we can consider the deflections of bearing elements and their effects on the contact stress there. So I've talked very broadly about Romax. Now Romax is actually, as it says at the top here, is a product suite. So we have a number of products, and to be quite honest, they all look and operate very similarly. And some of them operate in exactly the same environment, but they're targeted for different users. So now within large OEMs, it's gone are the days where you'd have just a person doing a transmission design. They have experts in lots of different fields. They have experts in gears, gear design, analysis. They have experts in bearings. They have experts in efficiency. They have experts in MVH. And the software has been designed to allow people like that to operate with the software. We do also allow for the generalist to use the software and use all the functionality within the same software package. So what we find is we have a portfolio of products. The first one we have here is from the design phase is Romax Concept. So it's more of a stripped back version of the software that allows quick modeling of different concept layouts and generating some basic results. It also has features in there to introduce sort of vehicle level performance. So when we're designing a transmission, maybe you have multi-speed transmission, you might want to select your ratios for a certain engine rev drop for each ratio, and this will allow you to specify gear ratios to achieve that. So it's a very lightweight version of the software for doing lots of different designs. We have Romax Evolve, which is designed specifically for electric machine designers. So it considers the electric machine, considers the deflections of the parts, allows you to put in Romax bearing models, and also run MVH and efficiency analysis of the motor. I should say that Romax is not an electromagnetic tool. So it doesn't calculate the electromagnetic forces. It just uses that data to drive the system model. We have Romax Energy, which is based for efficiency calculations. So we can do things like bearing loss modeling, gear drag, gear sliding losses in the mesh, seal losses, and we also have links to other software to do CFD analysis within the gearbox. Probably our what we refer to as our bread and butter of the software is Romax Enduro, which is all about durability analysis. So again, it's got the gear ratings, the bearing life calculations, shaft fatigue calculations, and general deflections of the model. It's also where we do a lot of the microgeometry analysis of the gears as well. Romax Spin is a really in-depth tool for bearing analysis. So this is primarily for bearing manufacturers. So it allows very detailed modeling of bearings and the generation of detailed bearing results as well. And then finally, we have Romax Spectrum, which is for MVH analysis. So this is our dynamic solver, which is a frequency-based solver. So effectively, we take our Romax model and we excite it with a sinusoidal signal. So it's like a forced vibration problem spring mass damper system that we use. And it's really for speed of dynamic analysis to be used in the design phase. So those are the software products, and I've given you kind of a very brief overview of the software. So I think it's probably appropriate to show you the software and show you how to use it to create a model. This is the Romax software, and for the different packages, this software will look exactly the same, and it's more of a licensing function which changes between the different products. So at the moment here we have Romax DT, which allows me access to all the Romax products. But over here, we have Enduro, we have Spectrum, we have Energy, and we have Spin. So we can switch between the different products within this same environment. So I'm going to create a new model for us to start. So again, just create new model. The one thing it asks here that I'm going to include to show later on is I'm going to include a lubricant. So at this point here, we can give a lubricant to our model. This isn't the only place you can define it. You can change it later on within the model, but I'm just going to just put in a synthetic ISO 100 oil into the transmission. Okay, and as we bring up our model, I'll talk you through the layout that we see here. We have the tabs at the top here, which go through obviously file functions, the modeling functionality within the software, loading, which is defining sort of point loads or torques and speeds into our model. The analysis option just allows us to run various analyses in the model, and the reports are obviously just generating the reports that we have within our model. Then we have the various tabs that will open up on this screen. They are detachable, so you can just double click on that there and it will detach into another one if you're working with multiple screens. That makes it nice and easy to have different things open. Just bring that back up. And yeah, we can flip obviously between the 3D view here and the 2D view here. And the 2D view is where you tend to do a lot of your modeling and where I'll show how to modify things in here. And then on the left, we have our assembly tree. And this is where when we create things, they'll all appear in this assembly tree and we can navigate through the different things there to open them up. And usually for various things on here, we can open them up by just double clicking on the items. Okay, so the first thing I'm going to do in our model is I'm going to create an electric machine, which might be an arduous task, but within Romax, there is a very simple wizard that we can go through to create the basic components of an electric machine. So I'm going to create this wizard here. And then essentially we're going to design from scratch, but should you have a third-party software that can export a file that we can read, you can actually import those from these various software files. So mop file, I believe, is from MotorCAD, and obviously this JMag Express file can be imported as well. But we're going to start from scratch here. So the first thing here is it's going to ask for some leading parameters, like what's the axial length of your stator? So in our case, 65 millimeters. What's the outer diameter of our stator? It's going to be 89.85. The bore diameter, I'm just going to leave at 50. Air gap, which is essentially the distance between the stator teeth and the rotor. I'll leave that at 1 for now. Number of pole pairs, again, is a function of the motor, and number of slots, which is the stator teeth, effectively in our motor. We're going to set to 30 there. In this case here, we can actually enter some performance data like efficiency or torque speed maps of the motor that we could then use later on in our model. So I'm going to enter that data there. It's then going to ask me about the rotor shaft. So we can say, what's the diameter of the shaft? In this case, it's 18 millimeters. What's the span between the bearings? So the rotor shaft will have 2 bearings on it, which will support it either end. And this is going to suggest, okay, what's the distance between those 2 bearings? So in this case, it's 89.5. The bearing offset, again, it's suggesting where those bearings sit relative to the center of the shaft. So in this case, it's 1.95. The extension, again, is the distance from the bearing center to the left or the right. So if you've got your rotor that's protruding out of the end of your casing, you might want to add an extension here. So on the left, it's 6.5, and on the right, it's 35.8. We can change the material of the rotor shaft here as well in this wizard. Then when we come to defining the bearings, we have the option to use stiffness bearings, which are sort of concept representations of bearings. So they're free to rotate, but they are linear. They have linear stiffnesses. Or we can go to the catalog. So in Romax, we have a catalog of bearings. So if I press select, so we can see here the different bearing catalogs that we might have, and we can choose from the various bearing types in here. So what I'm going to do is I'm going to choose the SKF bearing catalog. I actually know the designation, so what the name of the bearing is for this one. So it's a 6003 bearing. So if and I know it's a ball bearing, so here we can filter by different bearing types. It's a ball bearing. So I'm going to filter there, and we can see all the SKF 6003 bearings. And I want to use this one here. It's a popular bearing because it says popular item over there, so it shouldn't have problem finding it from a supplier. And then for the right-hand bearing, I'm going to do exactly the same, but this one's a little bit bigger. So I'm going to turn off all these filters it's taken. So this is 6005 bearing. So again, there we go. We can accept that bearing there. Okay, and then, so that's the shaft of the rotor. The next bit is to define the actual rotor itself. So the rotor itself is just be a component, a lumped mass with some inertia attached to it. So in this case here, it kind of knows the length. It knows the bore diameter because I've specified it, and it knows the outer diameter. So we can sort of just treat it as a cylinder and estimate the mass and inertias. So that's what I'm going to do. Just going to estimate those values there. The next option is the stator. So again, some of these parameters are taken from things I've already entered. So we already know what the inner diameter, outer diameter, and the active length is. The slot height is effectively the height of the stator teeth. So in this case, I'm going to make them 8 millimeters, and the air gap is at the bore diameter of the stator. It's the gap between the teeth. So I'm going to make that 1.5. We've already defined a number of slots. We can change the material here if we wanted to. And axial divisions, if you've got some skew in your rotor. So rotation of your magnets as you go along the axial length. So at the moment, I'm not going to do that. We're just going to have one definition of the rotor going along. And then finally, we're going to create a housing around the stator to hold the stator. So I'm going to create an outer diameter. I'm actually going to leave these to be the same, and I'll leave the material to be steel as well. Again, we could change that later on as well. And then here, we're going to convert this housing to be an FE component in here. So when I press next, the MVH tab here is if you want to add excitation data, if you wanted to do MVH analysis. We're not, so I'll just press finish at this point here. The one thing I'll say before I leave here is that the help file button at the bottom is a good way to go through and explain these parameters as you go through, so you can understand them in this window. So when I press finish, it's going to create the solid geometry of our housing. It's going to create a surface mesh, a volume mesh, and then it's going to sort of save that FE data for us. And it's going to put that into our model. So in a few seconds, finish, go. And then as we go back, we can see our electric machine is now being generated in our model. And again, we can go to our 2D view here, and we can see our housing that it's generated. We can see our rotor shaft and the two bearings, the rotor and the stator teeth there. Now in the in the gearbox assembly here in our assembly tree, we can see it's created an electric machine, it's created the housing, and it's created the rotor shaft. And the rotor shaft here also has within it the bearings, two bearings, and also this rotor which is attached to it. But obviously this might be a simplistic rotor shaft design, and we might want to update it. So what we could do is we could manually update this in this window. So we can add steps to our shaft. So if I click on this button here and I click in different areas, it creates sections of the shaft. And when we click on this, we can then start to change the diameter. We can change the position. Oh, I didn't mean to do that. I meant to do this. Change the position of steps here, and we could start to make it the shape that we wanted to. We can also double click on this shaft and make changes directly in this worksheet for the shaft as well. So I can select any section from this tree here, and I can make changes to the length, diameter, bore. I can make tapered outer diameters or tapered bores here as well. What I'm going to do, because rather than go through and create a very complex shaft for you, I have already created one, so I'm going to bring that into the model. So I saved this from another model, and what I'll do here is I'm going to right click on the gearbox assembly, and there's an option to import an XML. So this is a definition of a shaft profile. in this case. So I'm going to click on Import XML, and here you can see my rotor shaft, which I've already created. So I'll double click on this. There we go, and it hides it straight away. So it puts it outside of our gearbox assembly. So this is my new rotor shaft. So to bring this into our gearbox, what I'm going to do is I'm going to drag it into the assembly. And then once I've done that, you'll notice it's got a little question mark next to it, which is saying, I don't know where this shaft is positioned in our assembly. So again, just double clicking on this, we can see the shaft profile, the more complex shaft profile that's been created. We've also got this component position option here as well. So if I click on this, I can set the X, Y, Z position, or I can give polar coordinates if I wanted to, and I can choose which direction the axis is pointing in. So it's obviously got the principal axes, but you can also add a custom axis here as well. So I'm just going to put it in the 0 position because that's where it wants to be. And you might be able to see it sticking out the end here, this new shaft over here. But what we want to do is we've got these 2 rotor shafts now. We want to basically delete this. But first, before we do that, we want to move these components from this shaft onto this new shaft. And the way to do that is simply to right click on this, and we can go to our properties window, and we can go to our connections, where it shows that the inner diameter of this bearing is connected to the rotor shaft and the outer is connected to our housing. So I can just double click or press edit at the bottom here, and I can change this connection to the new rotor shaft. The position doesn't need to be updated in this case because it is where I want it to be. I'm going to press OK there and just accept that it's going to go. And you can see now it's moved that left-hand bearing under the rotor shaft here. So what I can do is I can click to the right-hand bearing. Just need to double click across there and then just move this across as well. Okay, and then finally, once that's updated, I will go to my electric machine rotor. There we go, and I'll move that one across. The electric machine rotor doesn't have an outer connection, it's just connected to the shaft. Go, I'm just going to allow that to update. And after it's done that, I'm going to close. And now I just need to delete this other assembly, which doesn't have anything in now. So I can delete this component there as well. And now if I go to my 2D worksheet, you can see that now we've got this more complex shaft arrangement with tapered sections on the outer diameter and the bore. Also in this one, my electric machine housing is a bit dull, a bit boring. So maybe we want to introduce a new version of that. Obviously, this is an FE component now. So to update the FE component, in the modeling tab, we can go to the FE data and import new FE data. So I'm going to import some new FE data. In this case, it is, you can see on the side, it accepts lots and lots of different file formats. In this case, it's a BDF file from Nastran. And I've called it new housing version 2. You can imagine version 1 didn't go down too well. So we've got version 2. It's just going to check through the data, specifically the elements that are in there, and also the material properties. So it tells us about what material properties that it's defined in here. So I can close this. I'm going to change the name because new condensed stiffness data ID blah 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 isn't very catchy. So we can now see the FE data here. By default, the rendering of this is just to look at the nodes, so the points. If we change to polygon, we can get a solid representation of that FE data. And in here, we can start to modify the position. We can rotate this FE data to align it better into our gearbox. But at the moment, I don't need to do that. So I'm just going to press OK. And after a few moments, we will see that the model has updated. And again, we can go to our 2D worksheet here, and we can see this new housing data has been introduced. The one thing that I didn't bring in with the housing is any stator information. So if I go in here and I hide my stator node set here, you can see that actually it's just a hollow area here. Now in Romax, you can actually create a model of the stator teeth and connect it to this housing. And that's what we'll do. It's called It's within the electric machine assembly, and it's called a concept stator. So at the bottom of here, you can see that we've got this concept stator here. And what we want to do is we want to add that to our gearbox. So we'll let it open up the window for this. And the first window that will show is actually a lot of the data we've already put in. We already defined the data for the stator when we were going through the wizard. So in this case here, it will just drag through the data, and it's going to create, hopefully after it's woken up, taking a bit of time. There we go. It's creating this 3D model of the stator. So again, we've got 30 teeth that is created at the bottom. The height here is 8 millimeters, which we defined. The gap at the bottom is 1.5. Outer diameter has been set, length's been set, inner diameter has been set. So we've got all that data for this 3D model. The next step is how are we going to connect it to our FE data already in the model. So I'm going to press next here. So what Romax is going to do is it's going to search around the outer diameter of this FE data, and it's going to try and take nodes from the FE data to map onto our model of our stator. So if I hide our housing, you can see here all the red dots. So these red dots here are nodes from the housing which get mapped onto the blue component, and they're sort of almost the seed nodes for the mesh of the stator. And then once that's been created, they're shared across the two FE data. So they're actually just merged together at these points effectively. So I'm going to press next. We don't have to update that data, it's already correct. And then finally, we're going to come in here and we're going to mesh this model. So if I create the mesh here, so it's going to generate the surface mesh on there, and then it's going to create the solid mesh and try and make the nodes align with each other. So generated the volume mesh, and then it's going to create what we refer to as a conformal mesh, conforming nodes on the stator here. So it's just adjusting the stator node position so that they are aligned with each other. Okay, and then once that's done, we've got that FE data, and I can finish here. You can add it to our model. Close this, press OK. See if I can update this. It might just require me just to bring the 2D worksheet again. It might update another point, but effectively now that will have the FE data in it. We can see that within this electric machine. By clipping the FE data, you can now see we have this stator within our model as well. Yeah. Okay, so that completes the modeling of our electric machine. Now we're going to start modeling our transmission. And what we're going to do for there is we're actually going to create a compound planetary arrangement. So this motor that I've taken here has got a top speed of 16,000 RPM. So we're going to need something in the region of 12:1 ratio to get the speed to something that's appropriate for the wheels. So trying to achieve that through a single stage or a single spur stage, single planetary stage is tricky. So one way to do that is to use a compound arrangement. So the way we do that in Romax is actually we're going to create two separate planetary gears and join them together. So here we can go to create our planetary stage and we can add our planetary assembly. We can attach that to our model on the center line. And then we can start making some changes. So the first thing we do is make sure the offset is correct, 136.3. And we are going to change the width of the planetary as well. So in this case, I'm going to make it 13. And what we can see here is it actually creates, once we've created that planetary assembly, it creates the planetary gear set there. It creates a carrier shaft, a ring gear shaft, and a sun gear shaft there. So by double clicking on either this planetary assembly or double clicking on this, we can open up and start making some edits to the planetary arrangement. One thing that I'm going to do here, I'm going to keep everything the same here. The only thing that I'd probably change at this point is if I wanted to change the number of planet groups, so number of planet gears within our assembly. But we're going to keep it at 3 for now, and we're going to create some planetary bearings for this. So the planetary bearings sit between the pin and the sleeve or the gear in our planetary system. And again, this allows us to choose whether we've got 1 or 2 bearings, and the type here. So I'm going to go to needle roller bearing, and when I press select here, it's actually going to open up our bearing catalog again. So in this one here, I'm actually going to search by some sizes. So it's going to be a 10, 14, 13 bearing. And if I apply the filter, only one will come up. It's this SKF needle roller bearing. So I'm going to accept that, press OK. And then the next thing I'm going to do is I'm going to convert the carrier to be a detailed representation. And what that means is Romax is going to create a set of shafts to represent each of the pins, each of the sleeves, each of the gears within that arrangement. At the moment, the planetary system is just put as one unit, and it operates as one unit in the model. So if I press OK on, well, sorry, let's get this right. If I press convert carrier in here, then what we'll see is that, I'm going to close this one now as well. What we'll see here is that Romax creates this sub-assembly here. So it's a group of other parts, and you've got the gear within there. And then we've got these 3 different sets. So they show on this end view here, the 3 sets. Now, this one is the primary set, and these ones are secondary. So they're copies of this first one there, which can be seen by this little red symbol of 2 people holding hands next to each other. And in here, we've got our pin in the middle and our sleeve between the 2 parts there. And we can start to edit these parts here. So the one thing I'm going to do to start off with is I'm going to change the PCD of this part. So I'm going to make it 92.5 millimeters. There we go. And now I'm going to open up our planetary system and start making some changes to the gear design. So in this planetary system, the first thing I'm going to do in this concept system, I want it to be a sun meshing with the planet gears, but I don't want a ring gear. So in the layout, I can select my ring gear, my annulus gear, and I can remove it. So just completely delete it from the assembly. The next thing I want to do here is I want to increase the face width for my sun gear. So let's make that 14. And I want to add some backlash into my system. So I'm going to make it 0.1. 0.1, 0.1, 0.1. And then finally, we're going to start adding some tooth numbers to our design. So I know what the tooth numbers I want. We can select a ratio if we wanted to, but I know the tooth numbers that I want. So 19 and 43 are tooth numbers. Now, we get lots of failures on this side here. And that's because it's saying, well, I've set the center distance, I've set the PCD, which is our center distance. And it's saying basically for this tooth count and this module, it doesn't fit that space. So what we need to do is just go back to the loading design, and there's this option to re-estimate pitch diameters. So again, if I just click on that, you can see all the failures disappear. And what it's done is it's updated our module. Now, this module is not very nice, but we'll update that at a later time. But for now, this gear set will now work. So I've now created my concept gears. And what I might want to do is it's still got this ring gear shaft. There's no ring gear. So I'll delete this shaft because I don't need it anymore. And I might want to start to update this planetary sun shaft. So the one thing that it's going to do here, which is a bit annoying, is that the datum of this shaft's in a strange position. So I'm just going to update that here. So I'm going to use the datum position tool to update that to be 0. So it's 0, 0. The start of this shaft is the datum here. And in this 2D view, what we'll do is we'll just change the dimensions of this shaft here. So the length, we're going to make 22.5. We're going to make the bore diameter 8.75, and we're going to make the outer diameter 18.75. And then finally, we're going to change our offset as well. So the offset is going to be 122. Now, what it's done is actually, when I change the shaft offset, it's actually moved the sun gear to the right a little bit. So I'm going to bring that back into position by, again, selecting it and updating the position to where it should be. So again, we can sort of align that back into position there. So that's our first stage created. We're going to create the second stage now. So we're going to do exactly the same process. So I'm going to select, click on there. It's going to create my full system. Exit there. I'm going to update my position, 157.3. Update, and I'm going to make this 16 millimeters. I'm going to add the same planetary bearing on this side. Go. Apply filter. We're going to add that. It's okay. Again, we've got 3 planets there, and we're going to convert the carrier on this side as well. Go. Okay. And then again, it's got a different PCD. So we're going to change it to give it the same PCD as the other gear set. And then we're going to go into the planetary system. This time we're going to remove the sun gear because we don't want a sun gear on this stage. And we are going to, again, while we're in here, we're going to increase the face width of the annulus, put some backlash in to these gears. And under the concept design, we are going to, again, define our tooth numbers for our annulus and our planetary gears. And again, we get our failures, so we're going to re-estimate those pitch diameters as well. So now we have the annulus and the second stage done. We can delete this sun gear shaft because we don't need it. There's no gear on it. Delete that component. And we can start to make some changes to the ring gear. Again, check the datums in at 0. There, we will open up here. And this one now, we want a face width of 21, a bore diameter of 130, and a pitch diameter of 140, an offset of 146.8. which again will move this into the wrong position. There we go. So that now creates our planetary system for 2 of them. The problem we have now is that these are still unconnected. They're still separate parts in our model. So we've got these 2 separate parts there. And what we want to do is connect them together to make them at 1 unit. Now we can do that in this window as well by using the merge shaft sections option here. Now it might not be on this list by default, but you can edit that list by using the 3 dots at the bottom and adding components across to it. So what I'm going to do is I'm going to merge the carrier together. I'm going to merge the pins together just by clicking on the 2 components, and I'm going to merge the sleeves together between the 2 of them. Okay, and then we can start making some edits to this model here. So we'll update the carrier first. Now, when we merged these parts together, it actually created a step in the middle, which I don't want. So I'm going to delete it here. Delete that step. I'm going to change the length of the carrier. It's going to be 90 millimeters. I'm going to change the datum because, again, the datum's in the wrong place. And it's now created these parts here. So these planet carrier parts are what connects this shaft to those pins. And it creates 4 of those. So if every time we created a planetary set, it created 2, one on the left, one on the right, to support them properly. But because we merged everything together, we ended up with 4. So what I'm going to do is I'm going to set my data on my left-hand one. I'm going to delete 2 of the middle ones, and then come back and I'll update the right-hand one later on. So on this one here, the offset is off the end of the shaft. So I want to change that to be on the shaft. And I want to specify the position of all these connections. So I'm going to do that quickly there, and I'm going to add the same offset to those. So you can see on here how these are positioned there, and we could show on here as well the carrier shaft if we wanted to there. Close that there. Okay, so that's fine. It's going to just start telling me that I'm using this now to position things. So this should update the shaft section. And then I'm going to delete these other components, these 2 here. I'll leave this one to connect in a short while now. The next step I want to do is update the planet pin. So again, I come into this window here. It's got these 2 extra steps. So again, I can just press delete and delete these steps. There we go, can delete those. The datum's in the middle. So again, I want to reset my datum to be at 0. I want to change my length of the shaft to 69 millimeters. And I also want to change the material of the shaft. The reason I want to change the material is because we've got these bearings running on it. So I want to use a bearing steel on the shaft. So I've defined this bearing steel I'm going to use. Okay, for now, that's all I'm going to do to this shaft. I'm going to go now and update as well the sleeve. So again, we know that this bearing is connected to the sleeve, so I can select that bearing and then come to this and open up this part as well. So in this case here, I've got 3 steps, but I'm actually going to keep those 3 steps. First thing again, datum in the wrong place. So let's update that. And what we'll do is we'll use this option here to cycle through the steps and update the geometry of those. So this first step here, I'm happy with the length, not so happy with the OD. I want to change that to 61.7, and I'm happy with the bore. We can then go across to the next step in our shaft by pressing next. This one I want to make a bit shorter, 5.5, and the OD is going to be 23. Bore's okay. Press next. It's going to tell me that it's going to resize the shaft because I've changed the length. That's okay. And this final one is 21.5, and the OD is 21. Bore is okay. And then once you do that, press OK, and we update the general shape of the shaft. So this now, we've now updated the pin, we've updated the shaft shape. We're just going to position things now. So the way the sleeve is positioned is it's positioned by these bearings. So these bearings have a position on this shaft and they have a position on there. So what we need to do is update these positions of those bearings. So I'm going to open up this Planet Gear 1 bearing first, and I'm going to change the offset of this bearing. It's going to be 26.75. We can also change the outer mounting as well. But in this case here, it's actually a calculated value, so I'm not going to change it. So we know if it was eligible, this offset would be selected. So I'm going to keep that as it is. And then this bearing here, I'm going to update as well. So again, in this one, I'm going to change the inner mounting. For this one, it's going to be 48.25. And when I go to the outer mounting, you can see that this has been selected. So I can define the position on the outer one, which is 30.75. It's just complaining that both the bearings are called left bearing at the moment. So what I might do is I might open up this one and change its name to be right. Okay, the other thing I forgot to do at this point is for the Planet 1 sleeve, I need to change this material, the shaft of this shaft's material as well. So I'm going to change that as well to the end-to-end bearing steel. Okay, so we've now set the position of the pins, and what I need to do is just update these offsets. So when I change the datum, these offset of the pin, these offsets changed. So I'm going to bring them back to 8 millimeters. And then for this right-hand carrier, all I need to do is just change the offset. And this again would calculate where the offset on the pin will be, because it's obviously related to where the other carrier is as well. So I'm just going to do that. So that is effectively, we've managed to update our model. Oh, there's one last thing to do. The carrier shaft offset needs to change. And this offset is, try to remember what it is, 112.3 millimeters. So there we go. So now everything is aligned in our system. Again, this carrier shaft's a bit boring in terms of design. So what I'm going to do is I'm going to import some FE data to overwrite this. But first, before we do that, we need to convert it to be an FE representation. So there's this option here under the modeling tab to convert, and we can change it to an FE shaft. This would allow us to mesh this data. I don't really care about meshing it, so I'm just going to press OK. It means there's no mesh data associated with it. It's just got the components, but there's no FE data. And what I'll do is, again, go to FE, import FE data. This time, my file is the carrier shaft. It's going to ask me the units that we're using in the FE data. In this case, we're using SI units. Press OK. It'll bring up the positioning window again. So close this. We'll change the name. It's going to bring up the positioning window. And again, we're just going to change to be a 3D representation of the FE data. So we've got that there. And what we can do at this point is we can go into the FE and we can edit the connections. So we've got all these points that are connected to this data, and we can edit those connections here. And we can view the areas that we are connected from our Romax model to this FE data. And these are the points which will be used to create our super element and connection points for that super element. Okay, so I'm going to go back to the 2D worksheet again, and we can see again this shaft. The only thing that we've got left to do in this model before we can start running things is we're missing some bearings on the carrier at the moment. There's no support for this carrier, and also we haven't connected the rotor shaft to the sun shaft, and we haven't grounded our annulus. So what I'll do here is, for simplicity, I'm going to use a rigid connection. So it's just a rigid stiffness between different shafts. And I'll use this to connect the rotor to the sun shaft and connect this annulus to ground. So I'm going to do that by selecting this option. So I can select the rotor shaft first and then select the sun shaft, and it creates this rigid connection between the two of them. For the annulus gear, I can select the annulus gear and I can select this to connect it to ground. We can also, with this rigid connection here, we can use these quick positioning tools at the top. So I can align it to the middle of the section. There we go. And it changes that position to be bang in the middle of this section here. For the bearings, I'm going to mount one bearing on the housing of the electric machine and connect that to the rotor shaft here. And for the other bearing, I'm going to mount it on this location and connect it to ground. So for the electric machine, I'm going to open up the electric machine here and add my bearing. Here, again, we can go to our catalogue, and I believe it's a 61812 that I am after. So I'll press apply filters. We'll just select this bearing here. Perfect. And it's going to open up the bearing window here to position the bearing, name it, and all things there. So the inner mounting on the electric machine rotor, we want to give an offset to the center of the bearing, which is going to be 111.8. And then when we go to our outer mounting, you can see that the housing currently is ground, but we want to connect that to our carrier shaft. So we can select that from our list here, and it already calculates the offset on that housing there. So you've connected those two parts together with the bearing. It should pop up in this view. There we go. There's our bearing in this view. And again, if we go to our 2D view, we can see as well that bearing connecting the two parts. And then finally, we're just going to use this 2D view to add our bearing to this shaft, and we'll connect that to ground. And again, in this case, we're going to select 61911 as our bearing type, and we'll select that from our list here. And we can position that bearing on our shaft by selecting the shaft. And you can see here it's got a position of 80. So just double clicking on that and we can update the position, and that will then throw that to the left there. Okay, so this model again is 99% ready to go. The only thing we need to do now is start applying some loads to our model. So the rotor is our point where we apply our input torque and speed. At the moment, we've got nowhere to react it. So what we need to do is we need to add a power load to our planetary shaft. So if I go to my planetary shaft carrier here, the one thing I noticed here is it's created this spurious node group at the bottom. There's nothing connected to it. So here you can see that this node group is connected to this bearing. This one's not connected to anything, so I'm just going to delete that one. I don't need it there. What I'm going to do is I'm going to attach to this carrier a power load. So we can specify an offset for that power load. So we can define a position along the axis where that's going to be, or we can connect it to an existing node within our model. So we've got this bearing node here. So rather than create an extra connection, what I'm going to do is I'm going to connect this power load, which I'm going to call output power, to the same node as the bearing in a raceway. So it just applies a torque at that point then. So I press OK, and you can see it turns up in this one here as well. And it's got node group 9, which is the same as our bearing here as well. So now that we've got our model set up, we want to define some loads in our system. And that's when we move across to our loading tab at the top here. So here we can go create duty cycles, we can create load cases, we can define attributes or temperatures within our system. So what I'm going to do is I'm going to open up our load case grid. So we've got a duty cycle, which is created by default, but we don't have a load case. There's no load cases available there. So I'm going to go to our load case grid, and it creates a new load case. So I'm going to call this test load case. I'm going to create a duration of 1, temperature is going to be 70, 16,000 RPM, and a torque of 24 Newton meters, something like that. There we go. So now this model is ready to run. So if I was to press run on the top, the first thing it would want to do is create the super elements. Now for this model, it takes about 2-3 minutes, but it's 2-3 minutes of me just sat in silence. So I'm not going to do that. What I'll do is I'm going to open up a model within here, which has already been defined, and I'll start running some analysis. In this other model, I have also updated the gear geometry to be detailed, and I'll show you some of the results that we can get by doing that. But just to give you an overview, if I double-clicked on the planetary system and converted the gears to detail, it will take you through a wizard where you can start to define the detailed geometry of the gears and specifying lots of other parameters for it. And again, I would rather than me going through that in this session, there are good tutorials that give explanations about how to go through that process. So what I'm going to do is I'm going to open up the model I already have created. Shouldn't take too long to open up. So if I double click on that, we can see that we have our model. And if I go here, you can see that this gear set is turned green, which means it's detailed in the model. So I have my test load case in here. I can run my analysis by using this button here, or I can go to analysis and use the run load case button at the top. So I can run my analysis here. And it's just so it's already run the static analysis. It's just now running gear ratings for the various gear components. It comes up with some warnings, but mainly for my gear design. So in this window now, what we can do is we can first animate the rotation of the model. So we can start looking at the kinematics of the model and how it's rotating as it goes, turns around. We can also, from here in our reports, we can view the deflections. So in the deflection results here, the one thing that's not going to be deflecting at the moment is the FE data. And that's because all we know at this point is the deflection of the condensation nodes, so the connection points to the FE data. You have the option here to solve the FE data and work out what the deflections are. Again, it takes a minute or two, but a minute or two that I don't want to waste in this presentation, so I won't show that. But again, we can see the deflection of the planet pins here. We can scale those to increase the deformation to see what's happening in our system. So we can look at the system level deflections. We can also look at our shaft level. So here we can look at our shaft, and I can run. I won't rerun the analysis, but you can see here we can generate the forces which are seen on this shaft. The road shaft probably doesn't have anything too interesting in terms of forces, but we can also look at the displacements that are occurring on the shaft as well. For an FE point of view, so again, this carrier, if I look at the deflections, again, from this view, we can see the nodes and we can see the forces that are being applied to each of these points in our model. We can also, as well, down here, if we click on the model option here, we could then solve the FE data for this part and look at the FE deflections here. But this gives you some indication of the system level forces, moments, and displacements in our model. So that's on a system level. We can see that data, but we can also go into the component levels as well. So we can look at the bearings, for example. So if I select our bearings, we have our list of our bearings at the top here. And for each one of these bearings, I can click on any of the bearings. I can look at some of the speeds that they've seen in the bearings, any of the sort of fault frequencies. So if there's an error, if there's a defect on the bearing, how it will look. We can look at static load ratings. So what's the static load the bearing is seeing versus its allowable. So we've got a static safety factor of nearly 10, or we can look at the raceway contact stress and the safety factor on that. So there's quite a difference here. The reason being is that this assumes a certain loading condition, whereas this the static stress considers the misalignment as well in the system. Here we can see the component loads and moments on the bearing, the displacements of the inner raceway, outer raceway, misalignments in the bearing as well. And as we go to the bottom, we can start to look at the ISO 281 factors here. Again, this one doesn't have a lubricant set, so it's not giving us any factors, but if there was a lubricant, it would be able to show you all this data here. We also have the ability to look in detail at the bearing as well, so we can look at the element loads and the element stresses. Gives some options there. So in this case here, we can start looking at how the rolling elements are loaded, which ones are loaded. So this is a radial plot, and it shows individual rolling elements and the load they experience. We look then down to the contact stress on the inner and outer raceway. And here we can see the stress distribution, and you can start to see the misalignment in the bearing here by the angle of this contact. And this can lead to quite, extreme misalignment and extreme load can result in edge stresses, which can be problematic in bearings. And again, that's for the inner and outer raceway. For the gears, again, we can start opening those up, and we can look at the rating results here. So we can start looking at click on this results tab. So we can start to look at the safety factor for contact and the stress, and for bending, the safety factor and stress in bending for each of those. If we had a duty cycle as well, this is a single load case, but if we had a duty cycle, we could look into that as well and start doing like a minor sum for damage. There's also a detailed list here as well, where we can go into detail into all the factors that are being used to calculate the bending or contact stress results. The final thing I'm going to show in here from a results point of view, there's quite a lot of results that we can look into, is the microgeometry results. So we can define gear microgeometry on different components and understand how they affect the results. So in this case here, I'm looking at the microgeometry definition between the Sun and the Planet Gear 1. I can run the analysis on this load case, which considers the misalignments that we see in our gearbox. So in this case here, I'm going to look at the 3D, and we can look at the contact stress as we go through the contact. So what we're looking at here is the face width of the gear, so quite literally the width of the gear, and the roll angle, and this is for the Sun gear. So at the bottom here, we've got the root of the Sun gear, and at the top, we've got the tip. So what we can see here is that we've got misalignment in our gear set. So that's biasing the contact to one side. And also we can see as we look on this side, that as we go through contact, you can see the change in region from 2 teeth in contact to 1 teeth to 2 teeth in contact. So we can see that within our gearbox. And we can come in here and we can start to, I'm just going to, actually it's the right flank, I'm going to edit. I'm going to add in some modification. So I'm going to put in 5 microns of lead crowning. Okay, and then just for simplicity, I'm going to put in 5 microns of barreling as well. So barreling is a similar sort of modification on the profile direction. So if I run that one again, you can see it's quite relatively quick analysis to update. Here, we can now see the modification to the contact patch here. So probably 5 microns of crowning was too much. The contact patch is too small, and maybe barreling was a simplistic approach here. But you can see that that has a direct impact on the contact stress in our gears there as well. And you saw me changing a lot of numbers in the software. That's because Romax is generally like a parametric software. So what this also means is that we can do optimizations. So for here, I can do a parametric study. So change various parameters and see the impact on results in like a design of experiments type analysis. So there's lots of things that we can do within the software to help the design process. And you can get a lot of results and do a lot of refinement in the design process in an automated way. So I think that's a very whistle-stop tour of the software, but hopefully, again, I apologise, I seem to have ran over, but you can't stop me talking, so I'm sorry for that. But yeah, there's lots of information in the tutorials, and on that note, I think what I'll do is I'll pass it back over to Alex.
Great. Thank you so much, Reese. That was just really impressive to see all the things that Romax can do and how it can streamline power transmission design with planetary gears. Yeah, I would have students do math on the kinematics of planetary gears, right? Their motion, or load analysis on pairs of spur gears, but I wouldn't combine the two. But you can totally do that with Romax. That's great. So I want to point you toward some ways that you can go deeper with our software and find out more about how it can help you get an edge with whatever competition you're a part of. So if you're on a competition team, you should sign up for our student competition bundle. You do need to apply, but this is totally free. You would need to, perhaps do some work with Campus IT, depending on how things are licensed for you. There are a couple of options, but really, once you fill out the form, we will help you get through the rest of the way. That is our job. Now, if you're not on a student competition team, you're just here because you're interested in Romax or in other Hexagon simulation software. Great, welcome. We have a list of software that is available to you and to any student and any professor in the whole wide world for free. Unfortunately, Romax is not on that list, but we have software like Apex, Nastran, Powertrain, and Mark for finite element analysis, Atoms for dynamics, Cradle for CFD. Actra does acoustics, Digimat does some really interesting things with materials. So if you want to check out Hexagon simulation software, you definitely have options. If you want to learn about Adam's car, that is what we have coming up next week. And we have a little bit of a schedule adjustment in process, but you should plan on us offering a webinar for Adam's car, at least for the next 2 weeks. So August 7 and August 14. August 21, we are, a little bit TBD on the exact scope for that webinar. But the one coming up next week is really going to focus on, here's how you can use atoms to analyze a single suspension. And then atoms for the second one on the 14th, we'll be looking at full vehicle analysis. You can find out all about our webinars at our homepage, and I'm going to share links for this in the chat. You can find our recorded webinars on YouTube at MSC Software-Hexagon. And if you want to get reminders about what's going on, you can simply follow me on LinkedIn. I post a reminder about a week in advance of each webinar and then the day before. So that's how you can get our software, and that's how you can keep up with us. Reese, did you have anything more to say in closing, or?
So the only thing I was going to mention was that I appreciated that that's a fast-paced webinar to go through. There's a lot of information, lots of numbers going in. On the Sim Companion site as well, we will upload the complete model. We will upload some notes on how the model was created. And obviously you'll be able to access the recording and try and slow my voice down.
Yeah, and to clarify, the what I was calling the webinar homepage is what we would call a Sim Companion site. Oh, and I should mention that, let's see, I believe that we have the Sim Companion site public. Sim Companion sites are not always public, but this one should be. So yeah, if you just click the link that I put in the chat, you should be able to get there. The full model information we don't have uploaded right now, but it should be up by the time that this goes up on YouTube. So Reese, are you ready for Q&A?
Yes, let's do it.
Okay, great. And let me know if you need to tap out at any particular point, or if you're free to just answer whatever questions come up. We don't have a whole lot of questions from students, but Alex Rackinator and I have a few questions. We're just very curious about what Romax can do. So first, we have a question from a student, Zachary Leger. In off-road applications where loads are not linear or consistent, can this software be useful? And can I first try with like a really naive answer to that question? I'm sure that it could be useful if you just apply a really big factor of safety, and Romax will at least help you make sure that your kinematics are reasonable, that you're, ballpark in the right range for correct gear sizes. But I wonder if Romax can do a little bit better. And I'm especially thinking of Baja applications. Zachary's asking about off-road where, you're driving this thing over bumps and through mud and so on. What are your thoughts, Reese?
So yes, so Romax works on a static load case basis. So what we would tend to do in these applications where we have varying loading conditions is you take some time history data of torque, or if you're able to get that torque sensing data from a transmission, or if you can predict what that would be, so using Adam's car or something like that to predict the torque fluctuation in the drive shafts, then you can present that data to Romax as time history data, and it can convert that into a duty cycle of different torque bins, and each of those torque bins will cause a certain amount of damage to your gear set. So that's the traditional way of doing it. As you said as well, there is within certain components, gears for example, where you can apply application factors which account for torque fluctuations in the primary driver, so the engine, and the driven component, so the wheels, the road, the machinery, whatever you've got attached to the other end, and that would increase the load experienced by your gear set, and also derate your gears in that scenario.
And what you described about that connection with Adams is a great example of how our software is even more powerful when you're using multiple products together. They, for just about any two products, you can think of a way that you can connect them. There's some kind of integration there, and the ones between Adams and Romax are very robust. On that note, Reese, you had mentioned the term super element, and I wonder if you could just provide a brief description, especially for somebody who maybe is already aware of finite element analysis, but is used to doing that on a single part or a couple of parts.
Yeah, so a super element, effectively, even those simple FE components that we had in our model. So those components had 100,000 elements, 100,000 sort of made up of 100,000 little triangles, little tetrahedrons. So when you try and solve that in FE, that part has 300,000 degrees of freedom, in X, Y, and Z. So 3 times that many, might have that many, maybe even more than that. So to solve that takes a bit of time and a bit of effort. So what we do is we go through a process where we reduce that into the stiffness coupling between the nodes. So we connect to certain points. So the shaft will have a point that we want to connect to our FE. So we want to know what the relative stiffness between that point and another point in our model is. We don't care what's going on in between in the other points, but we just want to know what those are. So with a bit of matrix wizardry, if you wanted to go into detail into this, the process technically is called Guyan reduction. Is the process that you go through, and essentially it reduces that matrix from 400,000 elements down to the bits that you're interested in. So it's basically creating a stiffness coupling between the points of interest.
Great. And then Romax can, as I understand it, take that super element information. It's not itself doing finite element solutions, but it's able to treat that finite element model as just a couple of equivalent springs really, really quick and do, dynamic simulation based on that. Is that right?
That's right, but Romax does do some FE. So it doesn't. It's not a general FE stuff. So it does produce. It produces the super element for you.
Oh,
so
okay, great.
It will. So you connect up everything within there, and there's just a button which says condense, which is our word for create the super element. You press it, and it does all the condensation for you, and then you can use it within your Romax model. So it's all entirely within the software. You can use other super elements from Nastran if you've created them already, then you can import those as well. But yes, you can do it within Romax.
I have another question. So we see these lists of lubricants and bearings. Is that built into Romax, or do you have to import that?
No, they're all built into Romax in terms of there is a default list of materials, bearings, lubricants. There's various other databases there within there that get imported on the installation of the software. But in any of those databases, you also have the ability to apply your own definitions. So if you've got a lubricant that's not on that list, you can create it and add that to the database. With bearings, you can create your own bearings. I'm not sure if for a student competition, maybe that's going a bit too far, but hey, it's up to you. That you might want to just choose. You've got some rolling elements, and you wanted to make a custom needle roller bearing for a planetary system. You can do that.
That's awesome. That really streamlines design processes for power transmissions. That I mentioned the Excel sheets, but also like half the work was filling in Excel sheets and half was leafing through, the 1,000-page SKF bearing catalog.
Yeah.
So it's amazing that Romax can do that for you. I have a few kind of like high-level how-to questions, but I think it might be more helpful for you to just kind of point us in the direction of how we could figure this out on our own. So being able to import a power curve, like you might know what your power curve is for your internal combustion engine, or you've got these different test cases. I think that those might have been generated by default, but how would you modify those? How would you generate different test cases? Or how do you calculate what the gearbox efficiency is for the design?
Yeah, so
how would somebody go about learning those things?
So there are lots of tutorials. I mean, the list of tutorials for Romax is extensive and is very, very detailed. So they're all available through the Nexus portal, and there are modules for efficiency analysis. There are modules for microgeometry using FE data. There are core tutorials that go through a lot of the techniques that I've just shown in this webinar, but it goes from the basic analysis all the way to some of the more advanced features within the software. And as I said, the help file is also very in depth, and you can access that from any of the dialog boxes or just the general help file. So yeah, those are usually the best sources of information.
So the tutorials that you described, are those all accessible within the product help, or does it help to go through Nexus?
The tutorials are through Nexus.
Okay. Yeah, would you actually be able to take us, would you actually be able to take a couple of minutes to show us how to access Nexus and navigate to those tutorials?
Yes, that should not be a problem. So
awesome, thank you.
Let me get rid of that there. And so I'll just use my Nexus portal bookmark here. So it's nexus.hexagon.com. So once you get to there, so I already have an account, but you can register from here and register for an account on the system. And within the Nexus portal, we have our tech center. And in tech center, we have documentation. So documentation center here. We also have the Nexus community as well, which again, maybe I should sign in to showcase that as well. So yeah, so first of all, we can go to our technical center and we go to the documentation center. I'll open up there, and so I'll also go to the community on this page here as well. So in the Nexus documentation center, we can search all the different software products that we have in Hexagon. You even have things if you want to design cabinets for kitchens. We have some software for that. But under we have the Romax suites here. So what I'd usually do is just go to the Romax suite here, and then in here we have the tutorial packs for Enduro, Energy, Spectrum, and Spin. So the software I was using today, and in here we can select one of those software packages. So maybe we try Enduro. And then in here, we've got a list of all the tutorials that we can go through. So again, is an introduction to the software, building a model, gears, bearings, defining detailed gears, microgeometry optimization, gear root stress. There is, some of the FE tools we've got here, so they're all available on here. So if I went to the rolling bearings tutorial on here, it will give you an explanation of the software that we're using, has models, and we can download those models to be used for the tutorials. And then you can go through this process of throughout there and find information about how to create things, but also sometimes it will have information in there as well, to bit more nuggets of information about different options that you would have within the software as well. So yeah, as I said, the question that was about non-linear or non-constant loading of off-road. So there's this duty cycle generation tutorial, and this gives you an indication of how you could do that process within the software as well. If I come back to the community here as well, you should also be able to access groups within this community. So I will try and let it upload, because Romax does not appear on the first list. Within this page here, you should be able to, there we go, access the Romax community here, and you can ask questions. At the moment, it's still not a particularly active community, and so at the moment, if you ask a question, most likely what will happen is I will come on and answer it as we get things rolling. But I'm hoping that in the future it becomes self-sustaining, and people can help each other in the community. Awesome, thank you.
So I do see a couple of questions. Is there a CV joint design feature in Romax?
There is not. No.
Okay.
Unfortunately, no. There is something that's been asked. What we usually find from customers is that they kind of interested in the stiffness of the joint from an MVH point of view. So drive shafts introduce some quite interesting vibrations signatures into the transmission, and so they're really interested in the stiffness of it rather than modeling the kinematics of it in any great detail.
How about, can you implement a continuously variable transmission in Romax using a belt drive?
There is a concept level option within Romax as a continuous variable transmission, but not to a. It's more of like for setting up a layout, and it's probably got some things in there for efficiency, but it's not. Again, it's not a design tool for that.
So there are some things that Romax is a little bit limited in, but overall, it's just a really powerful product. Reese, thank you for taking the time to prepare this webinar, for showing us how to use Romax for design tasks that are really useful for Formula SAE, Formula Student, and similar competitions. Again, this webinar is going to be, posted on YouTube, and there will be more webinars to come. So, keep in touch, and I hope that the subsequent webinars are also useful for you. Okay, thanks a lot, Reese. I'll see you later.
Thank you very much, everyone. Cheers. Bye-bye.
Okay, bye.